Hello everyone. I assume you know how transformers are everywhere in AI and almost all LLMs these days. The secret sauce is the attention mechanism. However, it can be super slow and eating up tons of memory, especially for larger and larger models nowadays. That's where flash attention comes in. It's a game changer and one of the most important breakthroughs in recent years, in my opinion. It makes training large models dramatically faster and more memory efficient. Let's take a look together. Before we start, I want to say that this talk is relatively math heavy, at least some part of it is. So if you don't understand it, don't worry about it. It won't affect your ability to understand high level mechanism. It won't stop you from using flash attention modules in development. It'll be fun and helpful to follow, even if you don't fully understand. TLDR, just try to enjoy and have fun. Alright, let's start with how the CPU and memory works. As you can see, here's the pyramid. This is the hierarchical structure of a typical CPU. On the top, it has processes registries. It is very fast, it is very expensive. And on the down, there's the tape backup, which most of us don't use already. It's very slow, but it's very cheap. So the speed of the storage goes from fast to slow as you move from the top of the pyramid to the down of the pyramid. At the same time, the cost goes from very high to very low from the top of the pyramid to the base of the pyramid. If you have experience in data structure or algorithm interviews, you must be pretty familiar with the big O notations. It's used pretty frequently for time and space complexity. However, it could give you a false impression that memory is homogeneous when it is actually hierarchical, like the pyramid here. It also focuses on compute, but neglecting I/O, which can be more critical for I/O-bound performance. Computer memory hierarchy is a system where memory is organized into levels with varying I/O speeds, costs, and capacities. It typically consists of CPU registers, cache memory, main memory, secondary memories, and sometimes also tape storage. This hierarchical structure allows for fast access to frequent use data while utilizing cheaper and slower storage for less frequently accessed information. This is a block diagram of a basic CPU computer processor. The black lines indicate data flow, the red lines indicate control flow. In order to finish a computer program or instruction, the CPU needs to basically do two things. First one is fetch data from different level of memories, whether it's register, which is the closest, or cache, or main memory, or flash, or disk. The second thing is, after it fetched the data, it needs to process it. So if a program or task is bottlenecked at fetching data from different level of memories, we call it I/O bound. To optimize I/O bound task, we can improve data locality, improve the algorithm to reduce read and write, or increase bandwidth with better hardware. If a program or task is bottlenecked at actual computation or data processing, we call it CPU bound. To optimize CPU bound task, we can optimize algorithm to reduce computation and processing need. Now let's move from CPU to GPU. How does GPU memory works? Well, it's actually pretty similar. GPU memory is also hierarchical. SRAM is fast, IO-wise, and expensive, and it has very small capacity. HBM, high bandwidth memory, is cheaper and slower, but it's still faster than the traditional DRAM. The capacity of HBM is also larger than SRAM. When we usually say GPU is 40G or 80G, like this one, it's NVIDIA A140G GPU, it usually refers to the HBM. This is because most of the operation that we expect a GPU to finish relies on HBM. For I/O bound tasks, imagine if we can do more with SRAM and less with HBM, it will be a lot faster. This is because SRAM's bandwidth is more than 10 times more than HBM. On modern GPU, compute speed has outpaced memory speed, and most operations in transformers are bottlenecked by memory accesses. This means if you're doing training on transformer, most likely it's I/O bound. This is the main motivation for flash attention. Let's do a quick recap on transformer. This is the typical encoder-decoder based architecture. In the encoder, there's a multi-head attention block. In the decoder, there's a cross-attention block. There's a mask attention block. And if we dive into the attention block, this is basically what it does. Given a matrix of queries, keys, and values, this is the attention score. It basically does a matrix multiplication between queries and keys. and then it do a rescale and mask if needed, also a softmax to transform it to possibilities, and then do a matrix multiplication with values. This is the standard implementation of the attention mechanism. The problem statement is, given input sequences query, key, and value. All of them are matrix of real value. Dimension is n by d. We want to compute the attention output O. It's also a real values matrix. Dimension is n by d. Let's say query and key matrix multiplication is S. So we have possibility equals to softmax S. And both S and P are of dimension n over n. The output equals to possibility multiplied by V, the dimension is n over d. In those formulas, n is the sequence length, and for large language models, the maximum sequence length can be very large. For example, Gemini can already support 1 million. So n is a very large number. D is the head dimension for multi-head attention. It's usually a lot smaller, say 64 or 128. So this is the standard attention implementation. The matrix QKV is usually stored in HBM. The first step, we load QK from HBM and then we compute S. Afterwards, we write S to HBM. This is because S is too big to store in SRAM since its size is n over n. And then we read S from HBM, compute the softmax possibilities, and then we write P to HBM because P is also n over n. And then we load P and V by blocks from HBM and compute the outputs. And then we write the output to HBM. Let's do a memory I/O analysis for the standard attention implementation. Note that we're not doing flops analysis. We're doing memory I/O analysis, which focus on the read and writes. First step, load inputs QKV. Matrices are read from HBM into SRAM. So we have 3 HBM reads, and each of them is of n over d elements. For computing attention scores, S equals to Q multiplied by K. This matrix multiplication is for an n over n matrix. And because it's too big, we need to write it back to HBM. Because it's too large to fit in SRAM for subsequent operations like softmax. This is true especially for a large n. And for today's large language models, you can consider this always true. So the HBM writes is n square elements for writing S. Afterwards, we do compute softmax. We read the S matrix from HBM, and then we calculate the softmax probabilities. It is also n over n dimension. And for the same reason, we write it back to HBM for subsequent operations, like calculating outputs. So we have n square HBM reads and n square HBM writes. And lastly, when we do the compute output, we read the P matrix and V matrix from HBM and do calculations. The final output O of size n over d is written to HBM. So the read complexity is n squared plus n multiplied by d. The HBM writes is n multiplied by d for writing O. In total, the I/O complexity is big sigma n squared plus nd HBM XS. By the way, big theta means tight bound, where big O means worst case. So the total I/O is basically big theta n squared, since n is usually a lot larger than d. This is a high-level comparison I get from the Hugging Face FlashAttention intro. It compares standard attention implementation with FlashAttention's implementation in a pretty intuitive way. For standard attention implementation, we have to load and write multiple times from HBM to SRAM, and this is very costly from an I/O perspective. In order to calculate S, we have to load Q and K, and then write S back to HBM because the size of S is too big. It's n by n. And to calculate the softmax possibilities, we need to load S from SBM again, and after computation, we have to write P back to HBM due to the same reason. It's n by n. And for the output, we have to load both P and V and write O back after the calculation. In comparison, FlashAttention tries to avoid storing those intermediate results, especially for S and P, which is n by n. In order to fit into SRAM's memory limit, FlashAttention divides QKV into blocks. And as you can see, we have KJ, VJ is the jth block of K and V. And we also have QI, OI, LI, MI, that is the ith block of Q. LLM is intermediate results that we're going to cover in details later. In this way, we avoid writing S and P back to HBM. We just need to load k, v, q from HBM and do some extra calculation on intermediate states like O, L, and M. And after some computation, we just write the final result back. In this way, we successfully avoid storing n by n as NP matrix in HBM. Before we dive into the details of FlashAttention, I would like to clarify a few things briefly and then provide some extra context to help us understand the content later. First, I want to clarify between training and inference. FlashAttention's mechanism in principle can be used in both training and in inference. However, in this talk, the context is mainly focusing on the training part. And on the inference part, for example, flash decoding, we might cover it in later episodes. The second thing is about I/O analysis versus flops analysis. FlashAttention aims to improve memory I/O instead of flops, which is floating point operation per second. So we are analyzing memory access, read and writes, instead of computation need. Remember we did flops analysis when we went through KV caching in LLM inference in my transformer video. It looks very similar, but it has nothing to do with FlashAttention. By the way, KV caching is used in LLM inference only and not in training, because inference for LLM is usually autoregressive, and then KV cache is useful in that way. But in training, all the sequence is processed in parallel, since we already know the input, so KV cache is a lot less useful. The first extra background I would like to talk about is per row softmax. In the attention mechanism, specifically in scaled dot product attention, softmax is calculated per row of the score matrix S, since each row corresponds to a single query vector and its relationship with all key vectors. The purpose is to determine how much attention that specific query should pay to every key. Q is the matrix of query vectors, dimension is n by d, that is the length of sequence by length of attention heads. K is the matrix of key vectors, dimension is also n by d. For each query vector in Q, we need to calculate the attention scores against all key vectors in K. The resulting matrix S has dimension n by n. And in the matrix S, the ith row Si contains the dot product scores of the ith query vector Qi with all key vectors from K1, K2 all the way to Kn, where Sij equals to Qi multiplied by Kj. This represents the raw relevance or attention score of Qi and Kj, which is the ith query and the jth key. So softmax is applied to all rows, and the sum of all elements in a single row Si equals to 1, represent the probability. And just to remind you, softmax definition is for a given input vector S from S1 to Sk, the softmax function calculates the probability Pi for each element Si as follows. Pi equals to e to the power of Si over the exponential sum of e to the power of Sj. Now, given the softmax definition, you might think the implementation should be very simple. We just need to go through x 2 times. The first time is we want to get the denominator, which is the exponential sum. And in the second pass, we calculate the actual softmax for each position, since we already have the sum in the denominator. However, this naive algorithm won't fly for most of the production environment. This is because e to the power of xi will likely overflow the hardware limit. That's why we need to use safe softmax in most of the production environments. And the idea is also very straightforward. We don't want the value to overflow the hardware limit. That's why we minus the maximum x for all the x values. In this way, it will definitely not overflow. So instead of doing 2 pass, we have to do 3 pass. The first pass is we want to calculate the maximum value. And in the second pass, we want to calculate the denominator. And in the third pass, we calculate the softmax for each position. This is called safe softmax algorithm. With these extra backgrounds, I think we're now ready to take a look at FlashAttention details. The essence of FlashAttention is doing tiling. Standard attention needs multiple HBM access, since S and P is too big for SRAM. FlashAttention aims to improve this by doing attention calculation with tiling, which is breaking big data into smaller tiles. This is a diagram of what is tiling. We have D by N matrix K, we have N by D matrix Q, we have N by D matrix V. Note that K, Q, and V are broken into blocks. The block size is not N, it's not D, it's something else that I will cover later. You might get confused the size of the block is D by D just by looking into this graph, but it's not. So in standard attention, QKT is N by N, and we need to store this whole thing in HBM. In order to avoid that, we are calculating only the blocks. We copy the single block of Q, K, and V from HBM to SRAM, and then we compute the block on SRAM before outputting to HBM. There are several key points for you to understand tiling and flash attention. The first one is divide and conquer. The input matrices QKV are divided into smaller blocks or tiles. Next one is iterative processing. Instead of computing the full attention matrix at once, which is the dotted square, flash attention process these tiles iteratively. It loads a block of Q and a block of K into the much faster SRAM. The third one is partial computations. It computes the attention scores and the weighted sum of values for these blocks within the SRAM. The next one is online softmax. This is also very important. Flash attention recomputes the softmax normalization on the fly as it processes more blocks. It correctly normalizes the attention scores without approximation and without needing the complete QKT matrix, that is the S matrix. The last one is accumulation. The results from processing each pair of Q and K blocks are accumulated to produce the final output without ever forming the full intermediate attention matrix in HBM. We have already gone through safe softmax algorithm. However, it won't work for flash attention since safe softmax require the complete row Si to compute maximum value and subtract that maximum value when calculating softmax to avoid overflow. Flash attention is doing tiling, means breaking KV and Q into blocks to fit into SRAM, so it no longer have access to the whole row. Then in this case, what should we do? This is the 3-pass safe softmax that we have gone through in previous slides. As you can see, the first pass is friendly with tiling, since for each position I, it only uses information about I and I-1. The second pass is not friendly with tiling due to the dependency on Mn, meaning it needs the largest value for M. And the third pass is also not friendly with tiling due to the dependency on both Mn and Ln. So what if we can find a substitute denoted as Li hat for Li so that Li hat only depend on positions smaller or equals to I and Ln hat equals to Ln. If we can build this substitute, then we can totally avoid the second pass and make the algorithm closer to tiling compatible since we still have Mn here. The substitute is found to be Li hat equals to this formula. And given the recurrence relationship between Li-1 hat and Li hat, this is the deduction process if you're interested. We can easily get the new 2-pass safe softmax algorithm. Note that this is still not tiling friendly, mainly because of Mn here. For the first pass, for I equals to 1 to n, for each position we calculate Mi and Li hat, and for each position we only need information from ith position or I-1 position. And for the second pass, since we already have Ln hat, we can calculate Pi for each position with Ln hat and Mn. We call that S equals to QK matrix multiplication, P equals to softmax S, and O equals to P and V matrix multiplication. We have already gone through S and P, so now it's time to get the final result O. And in this process, we will make it tiling friendly and improve the algorithm further. The straightforward algorithm to calculate output based on the previous 2-pass safe softmax algorithm is as follows. The first pass for I equals to 1 to n, we calculate Si, Mi, and Li hat. And the second pass, we calculate Pi according to Ln hat and Mn, and then we calculate Oi according to Pi and V. The 2-pass algorithm uses kth row of O as example for simplicity. However, the computation of different rows are independent, so for other rows it should be identical. If we store the intermediate states Mi, Pi, Oi, and Li hat, and yes, we can store them in HBM given the small footprints and I/O cost, then this algorithm is tiling friendly. We call it online safe softmax. Can we improve this algorithm further so it has only 1 pass? The answer is yes. The main reason we still have 2 pass is because in the second pass, when we calculate OI, it has dependency with MN and LN hat, which requires the first pass to finish. What if we do the same thing for O and we construct OI hat that meets the following criteria? OI hat only depends on information from position smaller or equals to I, and ON hat equals to OM. And yes, we can find this math formula, and this is the OI hat. We can now merge two paths into one if we know the recurrence relationship between OI hat and OI minus 1 hat. And again, it's pretty straightforward for us to find out the recurrence relationship. This is the math deduction detail. Pause the video and take a look if you're interested. Finally, we have the one-pass FlashAttention algorithm that is tiling friendly. For that single pass, for each position from 1 to n, we calculate the SI first, and then we calculate MI, which is the maximum value up to ith position. And then we calculate LI hat and OI hat. And after we do n times, ON hat will be the final accurate output for the kth row. And this is tiling friendly because for each of the calculation, it only depends on the information of ith or ith minus 1. So now let's apply tiling to it. This is the detailed forward process for FlashAttention v1. It's pretty much the same as we've gone through in previous slides, only adding a few details. For example, it adds the block sizes BC and BR. And then we divide Q, K, V into blocks. Basically, each block of Q is BR by D, and each blocks of K and V is BC by D. And correspondingly, we also need to divide O into TR blocks. And then it has the outer loop and the inner loop. The outer loop is for J from 1 to TC. We iterate through keys and values blocks, and we load those blocks from HBM to on-chip SRAM. For each of the K and V blocks, we go through all the query blocks along with output blocks and L and M blocks. We load them from HBM to on-chip SRAM. The rest of the calculation is the same as we have gone through in previous slides. The diagonal function here is constructing a diagonal matrix given a vector, and the upper bracket here is a ceiling function denoted by upper bracket x, which rounds a real number up to the nearest integer. For example, 2.7 ceiling function equals to 3. And the outer loops is on k and v, and the inner loop is on q. Notice that this was later swapped for parallelism in FlashAttention v2, which I will cover in maybe next episode. The intermediate steps M and L are written to HBM for backwards pass recomputation, which I will cover in later slides. Now, let's take a look at the block size before we dive into memory I/O analysis for FlashAttention. BC and BR block size are picked intentionally to fit in all 4 blocks of QI, KJ, VJ, and SIJ into SRAM of size M. The dimension of SIJ is BR by BC, and based on the previous algorithm detail, we know that BC and BR is a ceiling function of this. So if we put those into this formula, BR by BC is smaller or equal to M over 4, which means we strictly control the size of S, so it won't exceed 25% of the total SRAM size. You can design other block size algorithm as long as it makes sure all 4 matrices can fit into the SRAM. Now let's take a look at the memory I/O analysis for FlashAttention. In the outer loop, each element of K and V is loaded from HBM once, so both are n by d dimensions, resulting in 2 multiplied by n multiplied by d HBM reads. So this is big theta n multiplied by d reads. Next, given K and V are broken into TC blocks in the outer loop, and we make TC passes in the inner loop over Q and O, each pass loading all of Q and all of O to HBM. This results in 2 by TC by n by d HBM reads. So this is big theta n d TC. The total I/O complexity is big theta n d TC plus nd equals to big theta n d TC. We can further simplify this if we make TC a function of n and d and n. Since Kj and Vj needs to fit into SRAM, the dimension of Kj and Vj is Bc by d. So we have this formula. Bc is of big O m over d. Similarly, Qi needs to fit into SRAM, and the dimension of Qi is Br by d. So Br is also big O m over d. Similarly, Sij needs to fit into SRAM, and the dimension of Sij is Br by Bc. So this is the complexity of Br. Then we have Tc equals to n over Bc, and the complexity is big theta nd over n. So the final I/O complexity for FlashAttention v1 in the forward process is big theta n squared d squared over n. Comparing with the I/O complexity of standard attention big theta n squared, since the typical value of d is very small, it's 64 or 128, and the typical value of n is very large, it's in kbs or mbs. So d squared is still a lot smaller than n. So FlashAttention requires many times fewer HBM accesses, leading to faster execution and lower memory footprint. This is a great intuition graph done by the original author in his blog, so I recommend you to take a look. Let's assume the whole K matrix only have two vectors. So in the outer loop, we're looping through all the K, which is K1 and K2. And for each pass, we go through all the Q for each K. So when we process K1, we have S1 equals to Q K1T. And we have the softmax function here, and we have the value here, and we get O1, the output 1, equals to this. And now, since we have to iterate n times, in this case n equals to 2, we come to K2. And in this case, we have S2 equals to QK2T and calculate the softmax. And then V2, we have O2 equals to this rescaling with the correct denominator from O1. Imagine now n doesn't equals to 2. It's a very large number. This rescaling to correct denominator process works the same for big n's. Just imagine this rescaling formula gets longer and longer. Now we have gone through the forward attention process. We should already know FlashAttention's motivation in the sense that is reducing memory I/O complexity. We should also know FlashAttention's mechanism, including tiling, online softmax algorithm. We should be comfortable using FlashAttention modules in development. Now this part about backward process is optional. Stay if you feel like it. Let's recap a little bit on what is backward propagation. The goal for training a neural network is to minimize the loss function, in this case, say phi. According to the chain rule, we use backpropagation to update weights for all intermediate neurons in the network. And assume forward pass is done and loss function is already calculated for the output, backpropagation starts at the end of the network. And the gradient of the loss function with respect to the neural network's final output is calculated first. In this case, let's call it DO final. O final is the final output and D is the derivative. And for any given intermediate layer, it takes the succeeding layer's DO as input and calculate current layer's updated parameters. So for the backward attention process, we have the current problem statement. Given loss function phi, and let the output gradient be DO, this is a matrix of real values and the dimension is n by d, and DO means loss function's derivative to O. We want to compute the input gradients, dq, dk, and dv. All of them are real value matrix and the dimension is the same, n by d. dq, dk, dv is loss function's derivative to q, k, and v respectively. Now let's briefly go through the chain rule. We already know q, k, v matrices are n by d. O is also n by d. dq, dk, dv is also n by d. We know S equals to q, kt. P equals to softmax S. Both of them are real value matrix of n by n. O equals to P and V matrix multiplication. It's n by d. So d phi over dv equals to d phi over do multiplied by do over dv. Since O equals to P multiplied by V, do over dv is P. So we have dv equals to P do. Similarly, we calculate dp equals to dov, dq equals to dsk, and dk equals to dsq. Now we need a little extra knowledge for the derivative of a softmax function. Softmax function takes a vector input and produces a vector output. Its derivative is a Jacobian matrix. The Jacobian matrix contains all possible partial derivatives of each output element with respect to each input element. Let y vector equals to softmax of z vector. We need to compute dyi over dzj for all I and j values. There are two cases to consider. There's case 1 where I equals to j, and then there's case 2 where I doesn't equals to j. The math deduction details is as follows. Pause the video if you need to take a look. The final output of combining both cases is this. When I equals to j, this is the derivative. When I doesn't equals to j, this is the derivative. So the full Jacobian matrix j of the softmax function is this. This can also be written more compactly using vector notation. It's basically diagonal matrix of y minus y multiplied by y transform. Now recall for the original problem statement we have P equals to softmax function of S. Given the Jacobian matrix for y equals to softmax S is diagonal y minus y multiplied by y transform, we have the following formulas. It's a detailed mathematical calculation of derivative S for each position I and j. Pause the video a little bit if you need to take a look. Now, with all those extra knowledge, we should be ready for standard attention backward implementation. When we do the backward pass, we already have matrices Q, K, V, DO, and P in HBM. We first load P and DO from HBM and then compute DV. And then we load DO and V from HBM and compute DP. We need to write DP back to HBM. Then we read PDP from HBM and compute DS according to the Jacobian matrix that we have gone through. And afterwards, we need to write DS back to HBM. Next, we need to load DS and K by blocks from HBM and compute DQ. The last step is we load DS and Q by blocks from HBM and compute DK. Now we have all DQ, DK, and DV. This backward process is typically requiring the matrices S and P. The size of the matrix is n by n. And just like the forward pass, due to the size of the matrix, we need to do a lot of read and write to HBM. Recall that one of FlashAttention's goal is to not store ON square intermediate values for the backward pass. So what should we do in this case? Remember when we talk about IO bound and CPU bound tasks? For transformer training, it's IO bound, which means if we can sacrifice a little bit on the CPU calculation and improve a little bit on the IO, it's actually a win. So that's exactly what we're doing. By storing the output O and the softmax normalization statistics M and L, we can recompute the attention matrix S and P in the backward pass from blocks of Q, K, V, O, and M and L in SRAM. This results in more flops due to recomputation. However, it still speeds up the backward pass due to the reduced HBM excesses. This is the detailed backward pass algorithm, and the recompute happens at this time. We recompute P with M and L, and the formula is the same as the forward pass. This is all the mathematical formula we used in FlashAttention backward pass. dV equals to PDO, so this is pretty straightforward. We have P, we have DO. Just do the multiplication here. This we already know from previous slides. Let's say if we define DI to be this formula, then we can simplify dSij to this. So we can rewrite dq and dk with the definition of big DI. Pause the video a little bit if you need to take a look at the details. Now let's take a look at the IO complexity. It's actually very similar to forward process. In the outer loop, each element of K and V is loaded from HBM once. Both are n by d dimensions. So this is big theta n by d HBM reads. And given K and V are broken into TC blocks in the outer loop, we make TC passes in the inner loop over Q, O, and DO, each pass loading all of Q, O, and DO to HBM. This results in 3 by TC by n by d HBM reads. So it's big theta n by d by TPC. And we can reuse the previous calculation for TC. The total IO complexity is big theta n dTC plus nd equals to big theta n dTC. So the final IO analysis for forward process and backward process is the same. And as we discussed, it's a lot smaller than standard attention since d squared is usually a lot smaller than m. Alright, this is the last slide I have for FlashAttention V1. Hopefully this is helpful, and I promise I will go through later versions of FlashAttention as well as FlashAttention's usage in inference in later episodes. If you liked my video, please subscribe, comment, and like. Alright, see you later. Bye.